On October 18, 1943, Flight Officer Carl Nelson faces two viable options, and neither guarantees survival. He is piloting a B-24D Liberator, serial number 42-40885, over the dense jungle of Papua New Guinea. The aircraft is returning from a mission in which weather forced the crew onto an alternate strike near Hoskins Airfield. Fuel gauges hover on empty. 4 Pratt & Whitney engines are living on fumes. One option is a full bailout. All 10 crew members exit at altitude, leaving the bomber to stagger on until fuel starvation ends the flight. That maximizes immediate crew survival, but it also leaves an uncontrolled aircraft coming down wherever physics decides. Another option is a split risk. Most of the crew goes out while the pilots stay with the airframe long enough to put it down with some measure of control. Nelson chooses that course. The order goes out. Credited with 35 combat missions with the 64th Bombardment Squadron, this airframe is a veteran, worked hard in one of the most corrosive environments on Earth. On this day, the mission profile had extended beyond the effective range of its fuel load due to weather diversions. Turning away from Port Moresby isn't panic. It's the last calculation left once the numbers close. Now the mountains stop being a viable crossing. The aircraft is forced toward a landing on the north coast side. At safe altitude, 8 crew members bail out. This reduces the human liability on board by 80%. It creates a new configuration. No longer a full crew combat platform, the aircraft becomes a heavy glider on fading power, flown by pilot Nelson and co-pilot Second Lieutenant John Pfieffer. The mission is not return. It is energy management until the surface arrives. This is a forced landing, not a crash. Control held to the last seconds. One job remains: keep the wing flying, bleed speed to the minimum, and meet the ground on your terms. The pilot effectively trades potential energy, which is altitude, for kinetic energy, which is airspeed, to keep the control surfaces responsive. If the pilot slows too much, the wing stalls and the aircraft falls vertically, resulting in catastrophic structural failure. If the pilot flies too fast, the impact energy squares with the velocity, ensuring the destruction of the cockpit. Nelson must thread this needle without engine power to rely on if the approach angle is wrong. The margin for error is measured in knots. Nelson and Pfieffer align the B-24 with a flat section of terrain west of Gona. They are not aiming for a runway. They are aiming for any stretch of ground that will not tear the aircraft apart. A choice that will prove to be a sago swamp under kunai grass. This terrain selection is deliberate. The swamp offers a long, flat runout area free of the hard timber that tears wings off in the jungle. However, the surface is fluid and unpredictable. Sago swamps are characterized by deep, organic mud and sharp, fibrous vegetation. Landing a tricycle gear heavy bomber in this medium invites the nose wheel to dig in, which would flip the aircraft over its back. The pilots configure the aircraft for the final approach. They are committed. 8 crewmen drifting under parachutes watch the bomber slide away beneath them. There is no radio confirmation of the outcome at that moment. The aircraft disappears into the tall grass canopy. 8 parachutes settle into the green, alive, accounted for. Now everything depends on how aluminum meets mud. For decades, the Liberator's final resting place was defined only by the memories of the survivors and the local villagers who saw it come down. There is no clear record here of a post-landing fire or explosion. The aircraft simply enters the landscape and stops. The location became a point on a map, reclaimed by the vegetation. The investigation of this site is not a recovery operation. It is a survey of a decision made in 1943. The objective is to verify the condition of the airframe and confirm the specific technical inputs Nelson used to put the plane on the ground. The swamp has held the evidence for over half a century. To understand the survival of the crew, we must examine the specific geometry of the wreck as it lies today. The difference between a survivable landing and a catastrophic breakup often comes down to the management of parasitic drag. Flight Officer Nelson and Lieutenant Pfieffer are gliding a heavy bomber with zero thrust availability. Every square foot of frontal area that strikes the airflow acts as a brake, stealing momentum and steepening the descent angle. To reach the sago swamp, the pilots must minimize this resistance. They make a critical configuration decision involving the propellers. In a glide, a windmilling propeller can become a brutal source of drag. To fight that, the pilots feather the 2 inboard engines, number 2 and number 3, reducing drag and buying precious distance. Feathering is a mechanical adjustment of the propeller pitch. The pilot activates a mechanism that rotates the blades along their long axis until the leading edge points directly into the wind. Instead of a flat disc fighting the air, the propeller presents a thin, knife-like profile. This collapses the drag signature of the engine nacelle. By feathering the inboard engines, Nelson cleans up the airflow over the center section of the wing, preserving the limited kinetic energy required to flare the aircraft just before contact. The second decision concerns the landing gear. A B-24D weighs tens of thousands of pounds even before fuel and bombs. Supporting this mass on small rubber tires requires a hard, compacted surface. The sago swamp is a suspension of water and organic matter. If the gear is down, the wheels will penetrate the surface instantly upon contact. This creates a fulcrum at the bottom of the aircraft. The momentum of the upper fuselage will rotate around this fulcrum, flipping the bomber onto its back and crushing the cockpit. Nelson keeps the landing gear from becoming a trap. Whether fully retracted or not, the goal is the same. Avoid a gear down touchdown that can dig in and flip the aircraft in soft ground. This distributes the impact load across the entire surface area of the lower fuselage. It converts the landing from a rolling interface to a sliding friction event. The aircraft enters the swamp. The smooth aluminum skin of the belly meets the mud and vegetation. The friction coefficient spikes immediately. The sago palm trunks and dense root systems act as energy absorbers, grabbing the metal structure and rapidly decelerating the aircraft. This rapid deceleration saves the crew, but it dooms the airframe. The physics of the breakup are dictated by inertia. The B-24 is a semi-monocoque design, meaning the skin carries much of the structural load. As the belly drags through the mud, the friction stops the forward motion of the wing box and the nose. However, the tail section, extending far behind the wings, still possesses significant forward momentum. That remaining momentum has to go somewhere. The fuselage bends, buckles, and tears as sections fight to keep moving. What stays in the swamp is a battered airframe, damaged by the landing, but not erased by it. The energy dissipates, the noise stops, the cockpit section remains upright and largely intact. The nose, containing the pilots, has not been crushed. Feathering buys the distance to reach softer ground. With the gear kept from biting, the belly slides instead of cartwheeling. The outcome is clear: 0 fatalities. All 10 men survive the sequence. Accounts describe the 2 pilots as unhurt in the landing. The bomber pays the price in crumpled aluminum, so the cockpit does not. The aircraft, however, is finished. The structure is damaged and the wreck sits embedded in wet ground. In the days that followed, U.S. Army personnel salvaged usable equipment, stripping the airframe of major components. What remains in the swamp is not a complete machine ready to be lifted, but a fragile shell held fast by terrain and time. The structural integrity required to lift the airframe as a single unit is gone. The break in the fuselage means the aircraft is already sectioned, but not in a way that facilitates transport. It is held fast by the suction of the drying mud and the rapid growth of the kunai grass. The pilots walk away to link up with the other crew members, leaving the Liberator to begin its new role as a static part of the geography. The loss mechanics are complete. The preservation mechanics now begin. Locating a 30-ton aluminum structure should be a straightforward exercise in modern remote sensing. A bomber has a magnetic signature, a thermal profile, and a distinct geometric shape that contrasts with the natural environment. However, the search environment north of Gona negates almost every standard sensor advantage. The primary sensor limit here is not resolution, but obstruction. It sits on the seam where swamp gives way to kunai. Kunai is a sharp, silica-based grass that grows to heights of 6 to 8 feet. From a satellite perspective or an aerial overflight, the grass creates a uniform canopy. It knits together over the wreckage, scattering light and creating a visual shield. A B-24D has a wingspan of 110 feet, yet in this terrain it is possible to stand 20 feet from the fuselage and see nothing but a wall of green vegetation. From the air, the canopy can hide the wreck in plain sight, so the method flips to ground truth. Boots in mud, hands parting grass, eyes on aluminum. In the late 1990s and early 2000s, aviation historian John Douglas documented the site with photographs, and a visit that helped fix the wreck's position in the modern record. The findings of this survey define the debris field layout we see today. The aircraft is not a scattered pile of shredded metal. It is a series of large, coherent sections held in place by the semi-solid terrain. The dominant feature is the nose and cockpit section, which sits upright. This confirms the survival of the flight deck crew. Aft of the wing trailing edge, the fuselage is severed. This break separates the tail section from the forward fighting compartment. This separation is the physical evidence of the whiplash loading event that occurred during the slide. The tail section lies slightly offset, twisted by the final torque of the impact. The swamp terrain dictates the accessibility of these components. The heavy sections, specifically the wing box containing the main fuel cells and the engine mounts, have settled deep into the substrate. The sago swamp does not just decelerate objects, it absorbs them. The mud has a high plasticity. Over decades, the weight of the aircraft presses the belly skin into the mire, creating a suction seal. This seal prevents the wreckage from shifting, but it also complicates any attempt to inspect the underside. The lighter components, such as the vertical stabilizers and the outer wing panels, float on the surface of the root mat. They are accessible but fragile. The dense vegetation grows through the lightning holes and around the rib structures, locking the airframe to the ground. To remove the grass is to risk pulling apart the corroded aluminum it embraces. Access is further restricted by the human landscape. The land belongs to the local villagers. Any survey activity requires negotiation and permission. This acts as a protective filter. The site is not open public land. It is a proprietary asset of the community living near Gona. This limits casual tourism and prevents the site from being picked clean by souvenir hunters. Production records list this aircraft as constructor number 1962, tied to serial 42-40885. The site documentation then works the other direction, verifying that the wreck in the swamp matches that identity. Identity is only the first lock to close. After the layout, the investigation narrows to settings, hardware that can't misremember. Start with the props. The validation of the pilot's competence lies in the angle of aluminum blades frozen in place. In the forensic analysis of an aviation mishap, witness statements can drift. Metal settings do not. The primary objective of a site survey is to compare survivor accounts with the hardware still sitting in the swamp. The critical evidence point is an inboard propeller hub. Without disturbing the wreck, the team documents the blade angle. The blades are not twisted into the chaotic signature of a powered strike. They sit in a low drag orientation, consistent with a feathered setting, the kind of choice that can stretch a glide just far enough to reach softer ground. This observation relies on a concept known as search geometry. In a dense, chaotic environment like a jungle or swamp, the human eye struggles to separate man-made objects from organic background noise. Nature rarely creates perfect straight lines, perfect circles, or 90-degree angles. Search geometry is the discipline of scanning for these artificial anomalies. It involves looking for the hard, linear shadow of a wing leading edge or the rhythmic spacing of rivets against the random texture of the grass. To confirm the identity of the aircraft, the survey team applies this geometry to the vertical stabilizer. The tail section holds the serial number, the definitive proof of ownership. The number is 42-40885. Finding this string of digits is a function of contrast. The original olive drab paint has faded and the aluminum oxide has dulled the surface. However, the yellow stencil paint used by the Army Air Forces typically has a different chemical resilience than the background camouflage. By carefully documenting what is still visible on the tail fin, the curves and lines of the numbers can be read. The 42 prefix identifies the fiscal year of the order, 1942. The terminal digits 885 link this specific assembly of parts to the 64th Bombardment Squadron and the mission log of October 18th. That correlation is the fingerprint, proof without possession. The blade angle, documented in situ, matters because it keeps context intact. Remove the prop for display and the evidence collapses. The survey confirms that the engines were managed correctly. It confirms the identity of the Nelson B-24. It confirms that the pilot's account of the fuel starvation and forced landing was not a fabrication to cover pilot error, but a documented procedural response to a mechanical reality. With the forensics closed, the story pivots. The crew lived. The airframe is identified, severed, and stable in its muddy cradle. Now, the question isn't what happened, it's what we do with it. Does this history justify the cost and risk of dragging 30 tons of aluminum out of a sago swamp, or is the respectful act to leave the evidence exactly where it lies? The decision to recover a World War II aircraft from a remote environment is not an automatic default. It is a selection process governed by 3 hard constraints. The first is the presence of human remains. The second is the rarity of the airframe. The third is the logistical cost of extraction. When we apply these filters to the Nelson B-24, the logic pivots away from recovery and toward preservation in place. The first constraint is usually the most powerful driver. If a site contains the remains of missing in action personnel, the imperative is forensic and legal. The United States government maintains a commitment to repatriate service members. In those cases, the condition of the aluminum is secondary to the recovery of the crew. Here, that driver is absent. There were no fatalities, and every man walked away. There are no bone fragments to sift from the sediment. There are no dog tags to locate. This fundamental fact changes the status of the site from a war grave to a historical artifact. The recovery operation shifts from a military necessity to a museum acquisition project. This introduces the second constraint, the condition of the artifact versus the cost of retrieval. The aircraft is a B-24D model, not rare in wartime production, but a rare survivor today. However, it is structurally compromised. As established, the fuselage is snapped, the wings are stressed. The corrosion state involves complex aluminum passivation, where the oxide layer is stable in the mud but fragile if disturbed. To remove this aircraft from the sago swamp would require a massive industrial effort. The site is surrounded by the dense kunai grass and soft terrain described in the survey findings. Standard heavy wreckers cannot drive to the location. The ground pressure of a crane would sink it immediately. The only viable extraction method would involve a heavy lift helicopter or the construction of a temporary road through the swamp. The cost of such an operation is measured in the hundreds of thousands, potentially millions of dollars. Furthermore, the act of lifting the wreckage risks destroying it. The wet, mud-filled wing sections are heavy. The corroded attach points may not support the load. Pulling the airframe out of the suction of the swamp could tear the aluminum skin apart, turning a recognizable relic into a pile of scrap metal. The third constraint is the security of the site. Often, wrecks are recovered to save them from looting. In accessible areas, aluminum is stripped for scrap or souvenirs. However, the hostile terrain north of Gona acts as a natural security system. The difficulty of access that hinders recovery also hinders theft. The local landowners provide a layer of human stewardship. The site is not secret, but it is not easy to reach. When we weigh these factors, the decision resolves itself. The risk of destruction during lift is high. The cost is prohibitive. The moral imperative of repatriation is absent. Therefore, the most competent engineering decision is to leave the aircraft in situ. This choice acknowledges a shift in aviation archaeology. In the past, the goal was often to drag everything back to a hangar. Today, we recognize that the context of the crash site is part of the story. The B-24 lying in the swamp tells the story of the fuel starvation and the forced landing better than a restored shell sitting in a climate-controlled museum in Arizona. The aircraft sits on land governed first by local communities and local law. Whatever its original ownership on paper, its real-world future depends on consent, stewardship, and the authorities on the ground in Papua New Guinea. It is a verified data point in the history of the 43rd Bombardment Group. The outcome is not a failure to recover. It is a successful decision to preserve. The final question is how long this preservation can last before the environment finishes what the landing started. The final state of B-24D serial 42-40885 is defined by a race between chemistry and biology. For over 80 years, the aircraft has sat immobile in the sago swamp north of Gona. While the survey confirms the structural history, the future of the site depends on the material properties of the metal itself. It remains recognizable because of aluminum passivation, the thin, oxide skin that behaves nothing like rust. In the jungle, steel corrodes rapidly because iron oxide, or rust, is porous. It flakes off, exposing fresh metal to the moisture, continuing the cycle until the object disintegrates. Aluminum acts differently. When exposed to oxygen, it forms a microscopic layer of aluminum oxide on the surface. This oxide layer is hard, chemically stable, and tightly bonded to the substrate. It acts as a sealant. Once formed, it prevents oxygen from reaching the metal underneath, effectively stopping the corrosion process. This is self-repairing armor. If the skin is scratched, the exposed aluminum reacts immediately to heal the breach. However, the swamp environment attacks this defense. The standing water and rotting vegetation create a complex chemical bath. The acidity of the organic mud can chemically strip the passivation layer. The growth of the kunai grass and sago roots applies mechanical pressure, prying apart riveted seams and trapping moisture in crevices where the oxide cannot reform. The lower fuselage, buried deep in the mud, exists in a different state. The dense anaerobic sediment blocks the supply of oxygen. While this prevents the renewal of the passivation layer, it also starves the oxidation reaction. This creates a preservation paradox. The parts of the aircraft that are swallowed by the swamp are often in better condition than the parts exposed to the air. The mud acts as a stasis chamber. This airframe is more than a study in corrosion. It is a tangible record of the 43rd Bombardment Group's operations in 1943. Before its final landing on October 18th, this specific machine flew 35 combat missions. It carried crews to targets across the Southwest Pacific. It survived fighter interception and anti-aircraft fire, only to succumb to fuel exhaustion. Leaving the aircraft in situ respects this operational history. A restored aircraft in a museum is often polished, painted, and stripped of its scars. It presents an idealized version of the machine. The wreck in the swamp presents the reality. The feathered propellers, the snapped fuselage, and the faded serial number are not defects. They are the primary source documents of the event. The survey-only approach adopted for this site accepts a hard truth. Documentation is the preservation that holds. By documenting the site, verifying the identity, and mapping the debris, we preserve the information without destroying the context. The Nelson B-24 will eventually disappear. The rate of decay is slow, but it is non-zero. The aluminum oxide will eventually yield to the acid. The sago swamp will eventually swallow the wingtips, but the investigation is complete. The decision to divert, the discipline of the bailout, and the competence of the forced landing are now locked into the historical record. The aircraft has completed its service. It does not need to be rescued. It stands as a silent, static marker in the landscape, a permanent witness to the crew who walked away in the war they fought. The pilots survived. The evidence is verified. The case is closed.